Now we will discuss some insertion operations in an AVL tree that require RL rotation. So consider the example is like this. We have 12 at the root and its right child is 44. So this is a balanced one. This is balanced AVL tree. Now if we want to insert 18, so 18 should be inserted here only to the left of 44. So here 18 is inserted. Now after insertion of 18, this tree becomes unbalanced. So let us check this one through the balance factor. So for 18 the balance factor is 0, for node 44 the balance factor is 1, for node 12 the balance factor is -2. So this node 12 has balance factor -2. So after insertion of 18, this tree loses its property of AVLness. So for that we have to balance this one by some insertion operation. So here you can observe 12 with the critical node, because it has the balance factor -2, that is not allowed. So 12 with the critical node. So from the critical node, if we move towards the newly inserted node, so the path is this one, right child, then left child, or insert we can write this is RL. So here we have to apply RL rotation. So this one RL rotation is the mirror image of LR rotation. That means we have to apply both rotations. So RL is equal to LL plus RR. So here RL rotation is equivalent to two additions, one is LL, then the next one is RR. So first which node we have to pull? So jump two steps from the critical node, that means one here then one here. So pull 18 in this direction for LL, pull 18 in this direction. So if we pull 18 in this direction, so 44 comes downward. So the new structure will be like this after applying LL rotation. So 12, then it's right 18, it's right 44. Now this is not balanced. We have to apply RR rotation on which node? On node 18, the same node. So here also applying, pulling here 18, here also we have to pull the same node 18. Now if we pull 18 here, that is the RR rotation, then if we pull 18, 12 falls here. So the new structure will be like this. So 18 becomes the root and 12 comes here, 44 comes here. So now this is the balanced one after applying RL rotation, or you can say after applying 18 or after inserting 18 to this one, we get the balanced AVL tree like this. Now we will take some more examples so that it will be more clear. So consider another example where 4 is at the root. So the root is 4, its left is 2, right is 6, its left is 1, right is 3, its left is 5, right is 7. Now here you can observe for 7 we have 1, right 16. So this is the given AVL tree. So here you can find the balance factor. All the nodes, the balance factor of all the nodes are 0, 1 or -1. So it is a balanced one. Now if we want to insert 15 to this AVL tree, so here 15 is going to be inserted. So 15 is going to be inserted to the left of 16. So you can find the path. Compare 15 with 4, move to the right. Compare 15 with 6, move to the right. Compare 15 with 7, move to the right. Compare 15 with 16, move to the left. So 15 is going to be inserted here only. Now after insertion of 15, find the balance factor. So for 15 the balance factor is 0, for 16 the balance factor is 1, for 7 the balance factor is -2. So here we can observe this node is the critical node, because in the path from the newly inserted node to the root, first we encounter node 7 that does not have the balance factor 1, 0 or -1. So 7 is the critical node, and from this critical node if we move towards the newly inserted node, the path is like R and L, that means right then left. So we have to apply RL rotation here. So this RL rotation is the mirror image of LR rotation. So first we have to apply LL rotation here, then again we have to apply RR rotation. So if we apply LL rotation here, or if we pull this node, then the 16 comes downward like this. So the partial structure is like 15 becomes the root and its right child becomes 16. So let us join this structure with the rest part of the tree. So if we join this one with the rest part of the tree, so the structure will be like this. So let me copy this one. Okay. So now here you can observe we want to join this one 15 16 with the right of 7. So right of 7, it is 15, it is 16. Now here you can observe this one is not balanced one. Again we have to apply the RR rotation, that means pull this node 15 in this direction. So if we pull 15 in this direction, so this 7 falls downward. So the new structure of this part I am considering. So the new structure of this part. So here 15 becomes the root, left becomes 7, then right becomes 16. Now join this one with the rest part of the tree. So let us copy the previous one. Okay. So okay. So now it is the rest part of the tree. We want to insert this one or join this one with this structure. So 15, left 7, right 16. So here you can observe 15, left 7, right 16. So if we insert 15 here, then after the balance operation or after the rotations, we are going to get the structure like this. Now we will take some more examples on this. Here consider 4 is the root, then left is 2, right is 6, its left is 1, its right is 3, 4, 6, left is 5, right is 15, then for 15 left is 7, then right is 16. So this is an AVL tree. So find the balance factors of each node. Here you can check. For 7 it is 0, 0, 0. For 5 it is 0. For 6 it is -1. This one 0, 0, 0. For 4, so it is 1, 2, then 1, 2, 3. So 2 minus 3, that is equal to -1. So this is an AVL tree because all the balance factors are -1 and 0. So that is allowed, no issues. Now we want to insert 14 here. So where 14 is going to be inserted? So first compare 14 with 4, move to the right, then compare 14 with 6, move to the right, then compare 15 with 14, move to the left, then compare 7 with 14, move to the right. So 14 is going to be inserted here only. So I hope this one is clear how this insertion is taking place, because we have discussed several examples of insertion in binary search, and also we have discussed several examples of insertion in AVL. So that's why I am directly inserting here. So 14 is going to be inserted here. Now after 14, find the balance factor. So all the balance factor of the roots that fall in the path from the newly inserted node to the root are going to be changed. So here for 14 the balance factor is 0. For 14 the balance factor is 0. For 7 the balance factor is -1. For 15 the balance factor will be -1. Then for 6 the balance factor will be, for 6 the balance factor we can consider this one, left is 1, then right is 1, 2, 3, so it is -2. For, so no need to consider the balance factor of 4, because here we get the, in the path we get the first node 6, which does not satisfy the required balance factor. So 6 is the critical node. So here 6 is the critical node. So from 6 or from the critical node move towards the newly inserted node. So here we have to follow the path like this. So it is right, then towards left. So if we move from 6 towards the newly inserted node, then the path is like RL. So we have to apply RL rotation to balance this tree. So for RL rotation we have to apply first LL rotation, then RR rotation. So move or jump 2 steps from the critical node for RL, that means this one first step, second step this one. So pull this node 7 in this direction or towards its left. So pull 7 towards its left. So if we pull 7 in this direction, then 15 this comes or this falls here. So if this falls here, so 14 is already there, so it shifts 14 towards its left. So the structure I am writing, the partial structure I am drawing here. So 7 becomes the new root, then its right becomes 15, its right 16 as it was. Now 14 is shifted here, and we have to join this one with the rest part of the tree, or simply I can draw here. So it is 6 and it is 5. So the rest part of the tree I am not considering here. Okay. Now again apply RR rotation, that means pull this one here in this direction. So if we pull 7 in this direction, then this 6 falls here. So the new structure will be like this. 7 will be the root, 7 will be the root, left is 6, then its left is 5 as it was, then here it is 15, so left is 7, 16 as it was. So the left of 15 is 14. So the left of 15 was 14 as it was. We are not updating this. Okay. Now join this part with the rest of the tree. So rest of the tree means I am copying this one only. I am copying this part. Copy, paste here. Then just we have to join this one with this part. So just I am copying once again this part. So copy and paste here. So here you can see this one is the final AVL tree after applying RL rotation. So this is the balanced one. Now we will see another example on this. So consider another example where 18 is the root, its left is 12, its right is 44, its left is 23 and right is 52. So now we want to insert 20 here to this AVL tree. So here before insertion you can find the balance factor. So the balance factor is like this, it is 0, 0, 0, 0 and it is -1. Now if we want to insert 20, so 20 is going to be inserted here only. So 20 is inserted. Now if we insert 20, after insertion find the balance factor. So here the balance factor is 0, here it is 1, here it is 1, here it is -2. Now 18 is the critical node here. 18 is the critical node because its balance factor is -2, that is not allowed in an AVL tree. So from this critical node move towards the newly inserted node. Newly inserted node is 20. So from this move towards the newly inserted node. So the path is like this. It is R and it is L. So from 18 we have to move towards its right. Then from 44 we have to move towards its left. That's why insert I am writing RL. So we have to apply RL rotation here to balance the tree. So RL rotation means it requires 2 rotations. The first one is LL and the next one is RR. So we have to pull 23 in this direction. So if we pull 23 in this direction, then 44 falls here, 44 falls here. So the structure will be like this. If we pull 23, so 23 becomes the root, its left is 20, right is 44, its right is 52 as it was. Now previously it was 18, then 12, the rest part of the tree. So now this one is not balanced, we have to apply again RR rotation. So for RR notation, which node we have to pull? The same node 23 in this direction. So if we pull 23 in this direction, then 18 falls here. So when 18 falls here, it has one left subtree already existing. So it shifts, when 18 falls here, it shifts 20 towards its right. So the new structure will be like this. So 23 will be the root, and its right is 44, its right is 52 as it was. Now 18 falls here and becomes the left child, and left of 18 is 12 as it was earlier. Now 20 becomes the right of 18. So this one is the AVL tree after rotation, or we can say this one is the AVL tree after inserting 20 to this existing one. So I hope this one is clear to everyone. So we have just discussed that this RL rotation is equivalent to LL plus RR. So we have to apply two rotations in RL rotation and also LR rotation, and LR rotation we have discussed, it is equivalent to RR rotation plus LL rotation. And for LL and RR only one rotation required, only one rotation, but here it requires two rotation, and this RL and LR are mirror images of one another, and LL and RR are mirror images of one another. So I hope all the rotations are clear to everyone. Now we will discuss another example of AVL tree. Like the nodes are given in this order, it is 63, then 9, then 19, then 27, then 18, then 108, then 99, then 81. So the nodes are given in this order, or the elements are given in this order. If the elements are given in this order, our task is to construct an AVL tree by inserting the following elements in this order. Now we have to construct the AVL tree using these elements in following order, inserting 1 1 in the following order. So here first is 63. So first create the node 63 in step 1. So in step 1 we have to create one node, and it is 63. Its balance factor is 0 here. Now in step 2, insert 9 to this node 63. So 9 should be in its left. So here the balance factor is 0, here the balance factor is 1. Now in step 3 we have to insert 19. So in step 3 we have to insert 19. That means 63 is here, it is 9. So 19 will be inserted to the right of 9. So after inserting 19, find the balance factor. So it is 0, it is 1, sorry, it is -1, then it is 2. So here this becomes unbalanced, and we have to apply this one left and right LR rotation here. So LR rotation means first pull 19 here towards in this direction. So if we pull 19 in this direction, what is going to happen? So 63 is at its original place. Okay, so let me draw this one here. So 63 will be the here now. Okay, so forget about 63, first come to 19. So if we pull 19 in this direction, then 9 falls here. So 19, then it becomes 9. So merge this one or join this one with the existing or the rest part of the tree. The rest part of the tree is like this. So now this one is also not balanced. We have to again apply the left rotation here. So if we apply LL rotation here, then 19 becomes the root, and its left becomes 9 and right becomes 63. So after inserting 19, the structure becomes like this. Now in step 4 we have to insert the next one, that is 27. So in step 4 we have to insert 27. Step 4 we have to insert 27 here. So what is the existing one? So existing one is 19, then 9, 63. So we have to insert 27. So where 27 is going to be inserted? So 27 will be inserted here to the left of 63. Then find the balance factor. So it is 0, it is 1, it is -1, it is 0. So all are balanced, no issue. Then in step 5, we have to insert. So we have completed this 63, 9, 19, 27, then 18. So now we have to insert 18. So if we want to insert 18, so the structure will be like this. So initially it is 19, then 63, 9, 27. So where 18 is going to be inserted? So first compare 18 with 19. So 18 is smaller, then come to the left because 18 is smaller, then here we encounter 9. So 18 is larger, so insert here to the right of 9. So 18 is inserted here. So after insertion of 18, again find the balance factor. So the balance factor here it is 0, 1, 0, -1, it is 0. So all are 0, 1, -1, so it is balanced, no issue. Then in step 5 we have to insert another element. So 18 work is over, we have to insert 108. Now where 108 is going to be inserted? So 108 is going to be inserted to the right of 63 here. So the structure will be like this: 19, 19, then 9, 63, 18, 27, then 108. So find the balance factor after insertion. So the balance factor here will be 0, 0, 0. This one is 0, it is -1, it is 0. So it is balanced, no issue. Then in step 6, okay, so this one is step 6. So this one is step 6. Now we have to move step 7. Step 1, 2, 3, 4, 5, 6. Now in step 7, so in step 7 we have to insert 99. So this one is completed. Now we want to insert 99. So step 7 we want to insert 99 here. So 99 where to insert? So compare 99 to here. So 99 is larger, move here, compare 99 here, 99 is larger, move here, compare 99, so 99 is smaller, move here. So 99 is inserted to the left of 108. So now insert 99 there. So here if we insert 99, so it is 19, 9, 63, 18, 27, 108, 99 will be inserted here. Now find the balance factor. So it is 0, it is 1, it is 0, 0, it is -1, it is also -1, it is also -1. Now in the next step we have to insert 81. So we have to insert 81. So where to insert? So 81. So compare here, 81 is larger, move to the right, compare 63, 81 is larger, move to the right, 81 is smaller, move to the left, 81 is smaller, move to the left. So 81 is going to be inserted here on the left of 99. So let me copy this one. Okay, so it is step 8. So in step 8 we have to insert 81. So 81 is inserted here. Now find the balance factor. So the balance factor will be here this one is going to be updated. So the balance vector 0, it is 1, it is 2, it is 1, so it is 1 minus 1 2 3, so it is minus 2, it is 1 2 minus 1 2 3 4, so it is also minus 2. So which one is the critical node? So like we have discussed, here 108 is the critical node, because we first encounter 108 if we move from the newly inserted node towards the root node. So 108 is the critical node. So from the critical node, if we move towards newly inserted node, so the path is LL. So we have to apply LL rotation, that means pull 99 in this direction. So if we pull 99 in this direction, then 108 falls here. So the new structure will be like this. So let me copy the old one, the rest part of the tree. So the rest part of the tree I am just copying, copy. Okay, now here you can observe it is 99 becomes the new root. So left is 81, then right is 108. Now again find the balance vector of each one after the rotation. So here it is 0 0 0. So here for 63 the balance vector will be 1, then 1 2, so it is minus 1. Then for 19 it is 2 minus 1 2 3, so it is minus 1. So here we are going to get this structure if we insert the elements 63 9 19 27, this one in the following order. So this is the AVL tree we get. So in this way also the question may come. So some elements are given and draw the AVL tree if we insert the elements in the following order. So I hope this one is clear to everyone. So now we are going to discuss how we can represent formally different rotations. So consider the structure of a AVL tree is like this. So we have one node K2, then its left child is K1, and for K2 the right subtree is Z, and for K1 the left subtree is X, or the left subtree rooted at X, and the right subtree rooted at Y. So like this. Now here if we want to apply LL rotation, so after performing LL rotation here on this tree, so if we apply LL rotation here, the structure will be like this. That means we have to pull this node K1, and because we are assuming that K2 is the unbalanced node. So if we apply LL rotation, then we have to pull K1 in this direction, then K2 falls here and it shifts Y towards its left. So we can represent in the figure like this. So K1 becomes the new root and its left subtree was rooted at X, no change here. Then K2 becomes the right child of K1, then the right subtree of K2 is rooted at Z, no issues here. You can observe the same thing here, same thing. Now this Y is shifted by, or Y is shifted towards its left as K2 falls here. So K2 left subtree becomes Y, or we can write like this one. So if we apply LL rotation to this unbalanced AVL tree, so after the LL rotation the structure will be like this. So this is LL rotation, here we can. So in computer's memory we have already discussed, we cannot pull a node and no gravitational force is there. So this pulling of node and gravitational force we are discussing for easy understanding. Now how we can formally write this in, or how we can write this using a method, or how we can write this in Java. So, how we can write this formally for its representation or for its implementation? How we can write this formally for its implementation? So, for the implementation you can write the method and assume the method name is AVL rotation, and it is going to return the node. So, after AVL rotation it is going to return a node. So, that is why I am writing here the return type is node and name of the method is AVL rotation, and it is taking as the parameter the critical node. So, here critical node is K2. So, node K2, and its the return type of the method is a node type, or it is going to return an object of type node. So, here you can consider node is a class. So, you can represent class node and some attributes you can write. Okay. So, now focus on this method. Now, here you can observe what is K2 is the input node here, K2 is the input node here we have written. Now, what is K1? K1 is the left of or left child of K2. So, that we can write here node K1 equal to K2 dot left. So, what is K1? K1 is K2 dot left. Then what is the next step we are doing? So, here you can observe this y, that is the right subtree of K1, or you can say the right child of K1, this y becomes the left child of here I have written both z and z. So, it should be y. Okay. So, here you can observe the right child of K1 becomes the left child of K2. Here you can observe this y was initially here. Now, this y after AVL rotation, this y becomes the left child of K2. So, we need to write that one here. So, K2 dot left. So, this one, this part K2 dot left. So, K2 dot left, this one will be the right of K1. So, we can write K1 dot right. Now, any other change? So, another change is here you can observe this K2 was here initially. Now, this K2 was the root. Now, this comes here, or this becomes the right of K1. So, we can write that one also, the K1 dot right, this one will be the K2. So, these are the 3 steps we have to perform for AVL rotation. Here you can observe. So, this one is step 1. So, we are finding this K1, what is K1 we are defining. Then in step 2 we are updating this y, and in step 3 we are making this K2. So, 3 steps we are just writing. Now, after the rotation we have to find the height. So, for that we can write. So, assume one attribute height is there in the class node. So, we will get to know about its detail when we write the complete program. So, K2 dot height equal to, for K2 its height will be maximum height of its left subtree and right subtree plus 1. So, which one is maximum, and we add plus 1 to the maximum. So, to find the maximum we can write math dot max. We can call the method math dot max to find the maximum value among 2. Then assume height is a method. So, you can write height of K2 dot left, K2 dot left, and height of K2 dot right. So, in this way we can find math dot max, height of K2 dot left, height of K2 dot right. So, from this, that means maximum height of this one and this one, which one is maximum, we will take that one. Then we are going to add plus 1. to the maximum height of y and z, find the height of y and z, which one is maximum, take that one and add +1 to that value to find the height of k2. So, here we are finding the maximum of k2 dot left and k2 dot right. Now, we have to add +1 to this value. So, +1. Now, we are going to find the height of k1. So, we can write this like k1 dot height equal to, so to find the k1 dot height, we have to find the height of x and the height of k2, and we are going to take the maximum among these two and add +1 to this. So, for that we can write the same thing, math dot max, then height of k1 dot left, k1 dot left, and height of k1 dot right. So, height of k1 dot right, that is height of k2. So, height of k2 we have already find here, or we have already got the height of k2 here. So, we can write here k2 dot height, k2 dot right height. So, find the maximum and add +1 to that. Now, we are going to return the new root. What is the new root here after rotation? New root is k1. So, return k1, we can write return k1, end of method. So, here you can observe the formal representation of LL rotation. So, it is going to return a node and the name of the method is LL rotation, and it is going to take the critical node as input, that is k2. So, k2 is the critical node. Now, after rotation what is going to happen? So, we are defining that k1 is the left of k2, and in step 2 this y, that means the k1 of right becomes k2 dot left. So, we are writing, or we are assigning k1 dot right to k2 dot left. Then in step 3 this k2 that was initially the root becomes the right of k1. So, we can write this one k1 dot right equal to k2, or we are assigning k2 to k1 dot right. Then we are finding the height of k2, we are finding the height of k1 and return k1. So, these are the steps, or this is the method to represent LL rotation formally. Now, we are going to represent the RR rotation. So, to represent formally the RR rotation, consider k3 is the root. So, we are considering k3 is the root node, its right is k4, then assume k3 left is A, its left is B, its right is C. Now, if we apply RR rotation here and we have to pull k4, and if we pull k4, k3 falls here and it shifts B towards its right. So, after applying RR rotation, we have discussed with several examples. So, k4 becomes the new root and its left becomes k3, its left is A, then it shifts B towards its right and it is C. So, after applying RR rotation to this AVL tree, the structure becomes like this. So, now we are going to represent this formally, or we are going to write a method for RR rotation. It is also going to return a node. So, we are writing node, then RR rotation, RR rotation, and it is going to take input the critical node, and here it is k3. So, we know that this RR rotation is the mirror image of this LL rotation that we have already discussed. So, here we have to first find k4. So, what is k4? So, k4 is the right of k3, k3 is the given as input parameter. So, we can write here node k4 equal to k3 dot right, k3 dot right. Then what is the next step? So, in next step, here you can observe in k4 dot left, B is here. Now, B becomes, or B comes here, that means it becomes the right of k3. So, similar to the previous one, this is step 2, this one is step 1, and In step 3, move K3 here. So, we are going to do the same thing. So, in second step, this B, so initially it was K4 dot left, make it to the right of K3. So, K3 dot right will be initially K4 dot left. So, initially it was K4 dot left and we are assigning to here. So, we are assigning K4 dot left to K3 dot right. We are doing the same thing. Then come to step 3. So, in step 3 K4 dot left becomes the K3. So, here we can write K4 dot left is going to become K3. Now, find the height. So, K3 dot height. So, here I am writing the same approach, K3 dot height equal to math dot max height of K3 dot left. Height is a method here. This height is a method and this height is a attribute. So, height of K3 dot left, then comma height of K3 dot right and add +1 to this. Now, to find the height of K4, so here K4 will be the new root. So, find the height of this one and height of K3 and take the maximum. So, K4 dot height equal to math dot max, then height of this C. So, height of C means K4 dot right, then height of this K3. So, height of K3 we have already defined here. So, K3 dot height you can write for that, comma K3 dot height, then add +1 to this. Now, we found the height. Then after that return the new root. So, what will be the new root? The new root will be K4. So, we can write return K4 here, return K4. So, this is the simple implementation of RR rotation. So, formally we have to write like this, and the pool of method gravitational force, that was for easy understanding. Now, we will move to the LR rotation. So, now we will discuss the formal representation of LR rotation. So, LR rotation. So, consider for LR rotation K3 is the root node and it is K1 and its left is A and here it is K2, its left is B, its right is C, it one is D. So, this is the initial structure and that is unbalanced, and K3 is the critical node. So, when K3 is the critical node in LR, so this is LR rotation, LR. So, when K3 is the critical node in LR, we have to pull this K2 towards its right, then again pull K2 towards the left. So, we have to apply two rotations, one is RR then LL. So, that is we have already discussed with some examples. So, I am drawing the final figure here. So, if we apply this LR rotation to this unbalanced AVL tree, the structure will become like this. K2 will be the new root and its left become K1, its right become K3, then its left become A, its right become B, its left becomes C, its right becomes D. So, I am directly writing the final structure. So, this will be the new structure here. If we apply LR rotation to this unbalanced tree, we are going to get this one. K2 will be the root, its left become K1, right becomes K3, its left A, its right B, its left C, its right D. So, this will be the new structure. Now, how to write formally this one? So, for that we are going to write the method is going to return a node. So, for that I am writing node and LR rotation, and it is going to take the input as the critical node. So, here critical node is K3. So, we are going to write LR rotation and the parameter is node K3. Now, what will be the K3 dot left here? So, K3 dot left is K1, and we are going to apply RR rotation where? On K2, we are pulling K2, that means we are going to apply RR rotation on K1 by making, if we consider K1 is the critical node and we apply RR rotation, we have to pull this one only. So, that we need to write here what is K1. So, K1 is the left of K3 and apply RR rotation by taking K1 at the critical node. So, if we apply RR rotation by taking K1 at the critical node, this node is going to be pulled here, because in RR rotation and LL rotation we are going to shift one node and pull towards left or towards right, but in LR and RL we have to shift two nodes and we are pulling. So, for LR rotation here we have to pull this one towards its right, or we can say take K1 at the critical node. So, that thing we are going to write. So, apply RR rotation where we have to apply RR rotation. So, RR rotation is going to applied on K3 dot left, and it is going to return a new node, and that node will be attached to this one, attached to K3 dot left. So, here we can write the new node that is returned after RR rotation will be the K3 dot left. Now, again apply LL rotation here only K3 dot left. So, on this node again apply K3, again apply LL rotation. So, again apply LL rotation where? On K3 dot on K3. Because if we pull this node here towards its left for LL rotation, at that time we have to consider this one as the critical node. So, by taking K3 at the critical node, we are going to apply LL rotation, and it is going to return a node, and that will be the new root, new root. So, return LL rotation K3, we can simply write. So, this is end of the LR rotation. Similarly, we can write RL rotation, because LR rotation and RL rotation are mirror images, we can say, or are symmetric. So, node RL rotation, and assume we are writing on the same K3, we are considering same K3 at the critical node. So, here we are writing K3 dot left. So, but here in RL rotation we have to write K3 dot right equal to, first we have to apply LL rotation, LL rotation and K3 dot right. Now, return RR rotation on K3. So, we have written formally the LR rotation and RL rotation. So, LR rotation is nothing but the application of two rotations or the combination of two rotations. LR rotation is nothing but the combination of RR and LL. Similarly, RL is nothing but the combination of LL and RR. So, this is all about the formal representation of different rotations in AVL tree.